This is a new section. This is section 3.3, which covers moments and fractiles. Moments and fractiles convey less information than a lifetime distribution representation, but they're often useful ways to summarize the distribution of a random lifetime. The lifetime distribution representations that were covered in sections 3.1 and 3.2, namely the survivor function, the probability density function, the hazard function, the cumulative hazard function, and the mean residual life function, they specify the entire distribution of the random variable t. Moments and fractiles don't convey the entire distribution of the random variable t, just one aspect or another. So one rather popular one is the expected value of t. Another one is the variance of t and its square root, which is the standard deviation. Another one is the median, t of 0.5. Another is the 95th fractile, sometimes known as the 95th percentile of the distribution. And interesting in reliability, sometimes you want to know these early fractiles of the distribution, such as the second fractile of the distribution, because that's corresponding to early failures. Now, in this particular section, the random variable t is going to be assumed to be continuous, and so all of the formulas that you see here will involve integrals. Most of those formulas you can simply replace an integral for a summation, and it will work out for discrete distributions. Well, first thing we're going to cover is expectation, and the expected value of some function u of the random variable t is given by this equation. So basically the next few slides are going to look at different things that can go in here for this function u of t. The most common thing that you're going to see for u of t is just t. And when you integrate from 0 to infinity of t times f of t dt, you get the expected value of t. Often the Greek letter mu is used here. It is often known as the mean time to failure. Now, because this is a positive random variable, the limits of integration go from 0 to infinity, but using integration by parts, you can show that this is also the area underneath the survivor function. And that relationship is true when the limit as t goes to infinity of t times s of t equals 0. So here are a couple notes on the mean. And if we're being careful here, we should include the word population mean here, because this is different, of course, from the sample mean. So the population mean is a measure of the central tendency or the average value. It is also the center of gravity in physics, abbreviated oftentimes MTTF for non-repairable items. Even though this is a term that people like to avoid, sometimes for a repairable item, they use mean time between failures. The reason this term is not used often is it doesn't tell you whether the repair time is included, and for that reason it's falling out of favor a bit. There are two other measures of central tendency, might as well mention them here. The first is the median, and again, if we are being careful here, we would call that the population median. If this is a picture of the probability density function, the median value, which is m, is that value so that there is an area of 1/2 to the left of m underneath the probability density function, and an area of 1/2 to the right underneath the probability density function. Another value is the mode, and that's where the probability density function achieves a maximum. On this graph right here, it looks like that maximum occurs about where that dot is, which means directly below it, that will be the mode. So 3 measures of central tendency: mean, median, mode, and the mean is the only one which is a moment of the distribution. The second moment of the distribution is the variance of the random variable t, and that is sometimes referred to as sigma squared. Here is its defining formula, and 2 or 3 steps of algebra will get you to what is known as the shortcut formula. For many probability distributions, that's a little bit faster. Some notes on the variance. First of all, it measures the dispersion about the mean. In other words, the spread of the distribution. If the distribution is very spread out, the variance will be large. If the distribution is tightly clustered about the mean, then you will have a small variance. The positive square root of the variance is known as the standard deviation, and that standard deviation has the same units as the random variable t. So if t is measured in hours, then the variance of t will have units hours squared, whereas the standard deviation will have units hours. The variance and standard deviation depend on the scale that you use. So if you use hours or if you use minutes, you're going to get different variances and different standard deviations. Another measure which shows up from time to time is the ratio of the standard deviation sigma to the mean mu, and that happens to be a dimensionless random variables because the units cancel. Problems with the coefficient of variation: it assumes different values for populations having identical variability but different means. So it is not the best measure of spread or dispersion, and also it's undefined when mu equals 0. Now that doesn't happen to be a problem in reliability, because if you've got a product which has an expected time to failure of 0, you're in trouble. Okay, other moments. Like to look at the quantity inside of this expected value, and that quantity is t minus mu over sigma. A lot of times this gets referred to only for the normal distribution, and the fact of the matter is it shows up for any distribution. Sometimes they call that quantity the centralized standardized moments. Centralized by subtracting mu, standardized by dividing by sigma. If you take this expected value across t and mu, of course the sigma can come out front as a 1 over sigma. The expected value of t is the same as mu, so this expected value is 0. So the first thing you see about this t minus mu over sigma is that its expected value is 0. Second thing that you see about it is, first of all, variance is a quadratic operator, so this sigma can come out front as a 1 over sigma squared. You know that when you shift a random variable, such as subtracting off its mean, that will not affect the variance, so this becomes just the variance of t, and you know that the variance of t is sigma squared. So sigma squared divided by sigma squared is 1. So this t minus mu divided by sigma is a random variable that has expected value 0 and variance 1. Once again, this often gets applied only to the normal distribution, but in fact this applies to all random variables. So for the third standardized centralized moment, you get something known as the skewness. The skewness is a measure of the symmetry of a probability distribution, And then when you go to the fourth moment, that is the standardized fourth central moment, sigma 4 is the expected value of t minus mu over sigma to the fourth power. This one has kind of a fuzzy interpretation. Sometimes it's a measure of the peakedness, and then sometimes it is a measure of the tail behavior of a distribution. Certainly, if you have a distribution with heavier tails, you're going to get a larger kurtosis. So that ends the general discussion on moments. Now we switch over to fractals of a distribution. This is the time to which a specified proportion p of the items fail. So example, the pth fractile of a distribution, and that's written as t with the subscript p, often called the pth quantile or the 100th percentile, satisfies the following equation. F of t sub p, which is the probability that t sub p is less than or equal to p, that is equal to p. This can also be written as t sub p is the inverse CDF evaluated at p. Now if you wanted to write this in terms of survivor functions, you could. T sub p can also be written as the inverse of the survivor function evaluated at 1 minus p. The p on t sub p denotes the left-hand tail probability. There are certain languages like R that consistently use the left-hand tail probability. The population median is denoted by t of 0.5, and that is in some sense in the middle of the distribution of the random variable t. The fractiles t.25, t.5, and t.75 have special names. Those are known as the quartiles of the probability distribution. So here's an example. The exponential distribution has a survivor function that looks like this. You may recall from previous examples that this lambda is a positive scale parameter, and it goes by the failure rate in reliability. What we want to do is we want to find the population mean, population variance, population skewness, and then also the pth fractile of the distribution. So first of all, to find the population mean, which can be written as either mu or the expected value of t, we're going to use that second formula that was given, which is the area underneath the survivor function. Well, the survivor function is just e to the minus lambda t, and when you integrate that and plug in limits, that's a couple steps here that were skipped, you get a 1 over lambda. Now to get the variance, we're going to be using the shortcut formula down here. So not only do we need the expected value of t, we also need the expected value of t squared. So that's going to be the integral from 0 to infinity of t squared times f of t dt, and that's going to look just like that for the probability density function for the exponential, which looks like this, simply by taking the opposite of the derivative of the survivor function. Using integration by parts twice, this turns out to be 2 over lambda squared. So when you come down here to find the variance of the distribution, you get the expected value of t squared, which is 2 over lambda squared, minus the expected value of t, which is 1 over lambda squared. 2 over lambda squared minus 1 over lambda squared gives you 1 over lambda squared, and that is the population variance. We're also looking for the population skewness, and that is given by gamma of 3, that is this quantity. That sigma is a constant, so it can come out as a sigma to the negative 3. And then for the expected value, basically you cube out this expression and drag that expected value operator across, and you get the expected value of t cubed minus 3 mu, the expected value of t squared, plus 3 mu squared, the expected value of t, minus mu cubed. This can be simplified somewhat, but since the only thing we don't know here is the expected value of t cubed, we're going to go ahead and just plug that in right here. So the skewness turns out to be this quantity, and the lambda cubed here, and the lambda to the minus 3's cancel, and you wind up with 2. Now to draw an exponential distribution here is time, and here is the probability density function. Exponential distribution looks like this. Its mean is 1 over lambda, and the fact that this came out positive says that in some sense the exponential probability density function is leaning to the left, leaning towards 0 in some sense, with the positive skewness there. If this skewness had instead turned out to be 0, that would imply you have either a symmetric or close to symmetric distribution. The pth fractile of a distribution t sub p can be found by solving, and this left-hand side right here is the cumulative distribution function, and you simply set that equal to p, and you solve for the pth fractile in that expression, and you wind up with t sub p is equal to negative 1 over lambda times the natural logarithm of 1 minus p. Finally, a little more practical example. The left-hand tail of the distribution of t is often of interest to reliability engineers because it corresponds to items sometimes that are covered by warranty. So let's say that engine failure, the time to failure of an engine, has a Weibull distribution with a scale parameter of 0.000077 and a shape parameter of kappa equals 1.2. Time here is measured in miles. Now, how we come up with these numbers is going to be by analyzing data. But in this particular case, we don't need to do that. We're just going to assume that these are given, and when we're out in Chapter 8, we'll see how you estimate those from data. So what we want to do is find the warranty period that would allow 1% of the engines to fail during the warranty period. What we really want to find here is the first percentile of the distribution. And the way we do that is we set the cumulative distribution function for the Weibull distribution to 0.01. And here is the CDF on the left-hand side of the Weibull distribution, and it gets set to 0.01. When you solve that for t sub 0.01, you get this quantity right here for any parameters lambda and kappa. But when lambda equals 0.000077 and kappa equals 1.22, this turns out to be 2,992 miles. So rounding that up 8 miles, if we set our warranty period to be 3,000 miles, that will be very helpful in determining the warranty claim costs associated with this engine.